Hello guys, welcome. So in this video I will discuss something I've already discussed previously, but from a very different perspective. And this I'll be using some analogies from, let's say, statistical physics and stuff, but it's nothing very, like, I'll be presenting it in a way which is non-technical, of course, because this is YouTube, not a statistical physics classroom, of course. But yeah, I mean, this is a very good, very important point, I feel like. I made a video, pretty recently, in which I said that I was basically talking about, if I remember correctly, hard work and smart work. I mean, a lot of people talk about hard work and smart work. Well, and what I claimed in that video was that there is no way around hard work. I mean, smart work is technical an illusion. I stand by my views. In this video, I'll be reaching the same conclusion, but through a different path, let's say. So this is, first of all, this is a path function, not a state function. Anyway, so, well, what I said in that video was that you should try to be the machine and not the magician, which makes sense because a lot of the times, we feel like, I mean, in my experience at least, I've seen people who feel like they cannot do it because they are just not made for it. Some people are born with, like, born genius or born like a prodigy or something. Some people can do it, but we can't. I don't know if there is any truth to it. Personally, I feel that's just nonsense. I mean, for instance, the main thing, whatever I'll be telling in this video is actually can be summed up in a single line, which Richard Feynman already said like years ago. I am an ordinary person who worked hard, who studied hard. That's what he said. That's what someone like Feynman said. He was an ordinary person who became Feynman because he worked hard. And you may say that, come on, he was just being modest. He was just being humble. I don't think so. In that sense, all of us are ordinary person. Even Einstein, in a way. Okay, Einstein was a genius and all. No, he was not. I mean, not in the sense we seem to think about it. He was different from the, let's say, from the ordinary man, from the common man. But it has also to do with the way he grew up and the way his mind works. It's not always just about some inherent talent or something. I mean, for instance, even Einstein, there are, I mean, I'm not very sure about the factual accuracy of this, but yeah, from what I know, Einstein was not very good in mathematics. I mean, there are some exaggerated stories saying that he failed in mathematics. I don't believe any of, I mean, no, he didn't fail in mathematics. I mean, he was a good student in mathematics, but when he was developing general theory of relativity, it was pretty advanced mathematics, of course. He needed the help of a lot of mathematicians to formalize the theory. But still, he is Einstein because he had the intuition, he had the initial idea of the, relating curvature of space-time with gravity and all that. The equivalence principle. That was a brilliant idea, brilliant insight. The mathematics comes later, but yeah, of course, you need the mathematics to formalize it into a theory. And for that, maybe a lot of mathematicians helped Einstein, but Einstein, the idea was Einstein's, right? I mean, so the thing is that it may seem like some people are just like a magician. I mean, they're just naturally good at it. No, come on, that's not true. I mean, some people like to play the role of the magician, so they will like act like, no, I am better at this, I am born for this. But in reality, it takes a lot of effort, trust me. It takes a lot of effort to be a magician. You, like I always say, we judge a magician by looking at, let's say, the magic show, which is, let's say, it runs for 2 hours or 3 hours. But to prepare for that magic show, to make sure that the magic show goes smoothly, the magician has to work hard. Not work smart, but work hard, practice hard, just like a machine. So behind every magic there is a silent grind, which I call machine. So it's just like machine versus magic. And I say, always try to be the machine. Maybe maybe you feel very stupid the first time you do it. No, it's not made for me. Try it, burn the midnight oil, just put in effort. And one day you will be the magician. You will know yourself that, no, I'm not a magician, I'm just a machine. I worked hard, that's why I could do it. But people will feel like, oh my god, he's a magician. That person was born for this. No, it's not. So, and I already said all of this in that previous video I was talking about. But what I want to talk, like, I want to, like, reach the same conclusions by a different analogy. I just wanted to share this analogy. Basically, that's the whole point of making this video. It's a good one. So statistical physics, I mean, you don't need to know like the technical details, but for instance, hard work and smart work. Well, I'm not saying smart work is not a thing. There is something called smart work which can be relevant at times under very special circumstances. But the idea that, no, you should not work hard, you should work smart, that is not true. Because to be able to work smart, First of all, you have to work hard for a significant period of time. Only then you can understand, you can figure out for yourself what is smart work. Because I mean, you have to know what is smart work. If you want to achieve something, there are a lot of ways to approach the problem. But to know which is the smart approach, to figure that out, must have a lot of experience. And experience, well, you cannot just have experience. You cannot just download experience on your brain just like you download an app on your mobile phone. For that you need hard work. Like I say, there is, at the end of the day, there is no way around hard work. That's what I firmly believe. So from a statistical physics point of view, hard work is like collecting ensembles. If you really want to measure an observable for a system, and if you want like a very accurate value, you need either an ensemble average or a time average, assuming you are dealing with equilibrium systems. You can which respect, let's say, detailed balance condition. You can say that, oh, this system follows ergodic hypothesis, ergodicity. By ergodicity I mean that, let's say you're measuring some quantity, some observable A of the system. So this is the system, it's evolving in time. So you measure A now, you measure A after 5 seconds, and then again after 5 seconds, and you keep on doing this a large number of times, like essentially infinite number of times. And then you take that, and then you add all these different values of A you get, and then you divide by the number of times you measure, and then you get an average value of A, which we call the time average, because you're measuring at different points of time. Now the thing is that this A is a fluctuating. That's the whole point of statistical physics. This A is a fluctuating observable. So we usually expect A to fluctuate around a mean value, but it still fluctuates. So right now I measure A, and if I measure the same parameters, let's say the same observable A after 5 seconds, I can get a slightly different value. I mean, if I'm sure that I will get the same value every time I measure, there is no point of taking the average. You'll get the same value. So if you know you'll get 5 every time, there's no point of measuring 5 times and saying, okay, 5 plus 5 plus 5 plus 5 plus 5 divided by 5. You know the answer is going to be 5, right? So there's no point in doing that. But that's not the case. So in reality, the value fluctuates a bit. Now, to get a very accurate estimate, you need a large number of ensembles. You cannot measure 5 times or 10 times. You need to measure a large number of times. Ideally, infinite number of times. In reality, I don't know. Maybe depending on the system, it could be something like 10 to the power 7 times, 1 lakh times, 1 million times, 1 billion times. So that is your hard work. You have to collect the ensemble. You have to collect the average values. For that, you have to be patient. You have to keep measuring. You cannot say that, oh, I'll just do smart work. I'll measure now. I'll measure after 10 hours. I'll just skip all the values in between. Come on, that's not smart work. That's dumb work. If you do that, you'll not get accurate value. There is no other way. Or you can also take the ensemble average, which is just a theoretical tool. I mean, an experimentalist cannot really take ensemble average. They usually deal with time averages. But if things are good and if the system is ergodic, then we can say that the time average would be equal to the ensemble average for all practical purposes. Of course, there is also the assumption that all microstates are equally likely. So what is ensemble average? You have a system right here, right now, and you want to measure this observable A of the system. You imagine, that's why I said time average is something we can actually do. You can actually take measurements at different time, like after intervals of time, but this is just an idea, but this is a very important idea at the same time. This is you have a system here, right here, right now, and you assume that there are infinite number of copies of the same system, and at one given instant of time. So in time average, you have a single system, you are letting it evolve with time, so you are changing the time. Right now you have large number of systems, but you fix the time, and at one instant of time you just measure this observable for all the systems, and you take their average. This is the ensemble average basically. Now you say that if I have the same system, I should get the same value. No, this is the thing. This is the thing about statistical physics. The value will not be the same. So when I say they are the same systems, I'm not saying you take literal copies of the system. No, you're not taking literal copies of the system. What you're doing is that on the large scale, the systems look identical. The systems are identical, but microscopically they're different. For instance, if I'm measuring the number of people in a room, just a very gross example, just to give you an idea. If I measure the number of my observable, let's say, is the number of people in a room, and let's say in a room, will this work, by the way, for the example I'm thinking? Okay. No, maybe not the number of people in a room. A better example probably would be, yeah. Okay, let's say we have the, okay. Let's say you're measuring the number of pairs in a room. This might sound a bit crazy, but let's say in a room you have 100 individuals. So how many maximum possible pairs they can form? 50 pairs. I mean, by pair I mean, okay, if you want, maybe like could be, I don't necessarily mean couples or let's say lovers or anything, but okay, if you want to think like that, you can. I mean, no problem. Just the point is just to give you the idea. I just came up with the example, by the way, so it sounds a bit crazy, but I mean, you can get. There is also a very good example. I could give an example with colors and the number of balls. The usual example that is given in introductory level statistical physics textbooks. But it's right now I'm just speaking. I am not showing you pictures, so I'll just stick to my example, albeit it's a bit crazy. So let's say what you're measuring is the number of pairs in a room, and how you characterize the system macroscopically is the total number of people in the room. So when I say that you have a system and you have identical copies, by copies I simply mean that all these copies have the same number of people in the room. So let's say in a room there are 100 people, and you have an infinite number of copies. So in all these different copies you have 100 people. So that's why they're identical. But what you're measuring is not the number of people. Of course, if you're measuring the number of people, there is no point in taking the average, because you know that since all the all the rooms have 100 people, I'll get 100 every time. So what is the point of getting 100 n times and dividing by n? I know the answer will be 100. No, there is no point in taking the mean if it's a deterministic value. That is how you characterize the system. Is they're identical. There are 100 people in every room, but what you're measuring is the number of pairs. So let's say in a room there are 50 pairs. There cannot be more than 50 pairs. So in a room everyone is paired up, 50 pairs. Another room there are 49 pairs. In another room there are 48 pairs. Maybe we allow that in no room. I mean, let's say, just to keep things a bit realistic, let's say it's impossible for 100 people to remain single in some room. So in a configuration where there are actually 0 pairs, it's very unlikely. So maybe there is something which is some energy or some attractive potential which is pulling people together. So usually we'd expect from 45 to 50 pairs. Let's say, just to give an example. So let's say you have an infinite number of rooms. Roughly in half of them there are 45, 46 or 47 pairs. In the other half there are 48, 49 or 50 pairs, and you want to take the average. So this thing, you're measuring the number of pairs, that can fluctuate a bit. That will not always be exactly 48 or exactly 49 or exactly whatever. So that's what I mean. So see, in this kind of situation, it's important to take the average, whether it's an ensemble average or time average. So hard work is that, taking the average. Without that, you will not get an accurate value. There is simply no way around it. What's smart work? Smart work would be, well, identifying what you measure. For instance, I mean, that depends on the system you're studying. That depends on your context. I mean, and for instance, the example I give makes no sense. But I mean, for instance, the question could be, should I measure the number of pairs in the room, or should I measure the number of single people in the room, or should I measure the number of people in the room? I mean, just to give an idea, that is smart work, because you can measure a lot of things in a system. You can measure a lot of things, but whether it's experimentally feasible, whether it will give you any new insights, whether it will, I mean, by measuring which observable can you get the most maximum insights in the most efficient way, figuring that out, that is smart work. But here's the point: without the hard work, if you are not ready to collect all those ensembles, I mean, all those average values, even if you figure out what to measure, your measurement will be incorrect. So that's what I'm trying to argue, trying to illustrate. There is no way around hard work, and that's the whole point of this video. But before I finish, now some of you will say that, but luck plays a factor. I mean, if I'm born in a very rich family, if I'm lucky, then even if I don't do hard work, I'm already at I have a head start, kind of, because I have a lot of money, I have a lot of resources. For someone who is born in a much, let's say, less well-off family, let's say a poor household, to reach to my level, they have to work a lot harder. So that's clearly not fair. That's a bias. I mean, I have an unfair advantage. That's true. But also at the same time, if I were to use a statistical physics analogy for this example, for this case, this is what I would say a bias, a bias toward the initial configuration. For instance, if you are studying, to give the very common example, I don't know, if you're studying, let's say, particles of gas in a box, and let's say your initial configuration is very biased. That means you start in a configuration where all the gas particles are huddled in the corner, just in a corner. And let us assume, just to make the example make sense, all the gas particles can attract each other. So if you're already starting in a biased configuration where everybody is close to each other, and on top of that they can attract one another, so then obviously, even if you let the system evolve, the gas particles will not spread out very effectively, because they attract each other and they're already very close to each other in the initial configuration. That's a biased configuration. So, and if we start with the biased configuration, even if you do hard work, even if you collect a lot of samples, you will still have a bias. I mean, to have a completely unbiased configuration, maybe you need to work a lot hard. That's the case of a poor person. So you have to collect huge number of average values only after a long amount of time. I'm talking about time averages right now. Only after a very long amount of time you can say that now the gas particles have like explored the entire box effectively, even if they attract each other. But if you start with a random configuration, like if the initial configuration more or less the gas particles are not exactly in a corner very close to one another, but they're more or less spread out, then even if they attract each other, you can get a lot of interesting. I mean, the system will explore the configuration space more effectively. What I mean to say is that the sampling will be easier. I mean, taking the averages will be easier. That's ideally how it should be, but unfortunately some people have the unfair advantage. So in real life, starting conditions are often biased, unfortunately. So of course, the same. So there is some truth to the fact that luck does play a factor. Lucky people need to give in less effort. But here's the thing: if you are ready to put in the hard, I mean, assuming you're unlucky, which is not a good thing, but okay, maybe you are unlucky in some aspects as compared to, let's say, compared to someone like Elon Musk, for instance. I mean, compared to someone like Elon Musk, we are all poor in a way. And by luck, I don't just mean your financial, like just from the monetary perspective. It could be anything. I mean, you know what I mean. But the point is, here's the important point. If you're ready to put in the extra effort initially, then you can speed up the process, how fast the system decorrelate. That means if you're ready to put in extra energy to pull the gas particles apart, even if the gas particles attract each other, then even if you start from a biased configuration where all the particles are huddled close to one another in the corner, even then they will very soon they will decorrelate. I mean, they will move away from each other and effectively they will spread efficiently. That's what I mean to say. So it's almost like if you were a physics student, you will understand. Otherwise, if you don't understand the exact details, it doesn't matter at all for the purposes of this video. So it's like the diffusion coefficient for your, let's say, for your master equation. Let's say you have something like a, I don't know, a fluctuation dissipation equation or something, I don't know. So your diffusion coefficient will scale as, I mean, your diffusion coefficient will have a positive correlation with the amount of effort you put in, because higher diffusion coefficient means the system decorrelates from the initial configuration faster. So the bias can only be in the initial configuration. Only the initial configuration is out of your hands. It's how nature throws you on this earth in your life, but that's out of your hands how you begin. You can take, I mean, maybe you're born in a rich family, maybe you're born in a poor family, maybe you're born with some disability. And that's let's say the luck factor, that's out of your hands. But how you go from there, that's not totally out of your hands. I'm not saying that's completely in your control, but at the same time, that's not totally out of your hands. So, and if you're ready to put in the hard work for the first few steps, let's say the first few years of your life, maybe, then you can overcome the bias in the initial configuration. That's what I mean to say. That means you can diffuse the system effectively and by this I mean you can diffuse your achievement so that you can be on par with the people who are born lucky, even if you are not born lucky. That's what I mean to say. Maybe it's unfair in a way because you still have to put in extra effort initially, but it's possible. That's what I mean to say. And now whether you are ready to put in the extra effort, or whether or whether you want to just complain for the rest of your life that no, I was born unlucky, nobody's gonna listen to you. I mean, you can, I mean, those are excuses, but you cannot give excuse. I mean, you cannot use those excuses and just justify yourself. I mean, you cannot run away from yourself with those excuses, right? Excuses are like kind of coping mechanism in a way, and maybe in some cases they can help you cope with society and with your peers, but not from you, never from yourself. That's why I say there is no way around hard work. Next and last point. Well, I mean to say that that's pretty much all I wanted to say in this video, but just one small thing I would like to say in the end is that hard work is like just put in the hard work. I mean it's not, I'm not trying to motivate you. I'm just, because motivation will not work. You have to understand there is no other way. And even after you realize there is no other way, if you're ready to live an average life, or and just keep justifying yourself with excuses and all, I work smart and blah blah blah, it's fine. I mean, it's your life, it's your decision. But if you really want to do something, if you really want to get shit done, there is no other way other than hard work. And if you work hard for a long time, then after a point, once you're experienced enough, you can have the right intuitions, you can work smart. But without hard work first, if you just keep saying that no, I work smart, I don't believe in hard work, I believe in smart work, that statement makes absolutely no sense to me. That doesn't make sense actually. Okay, so I mean, yeah, there is no other way to smart work. The people around me might be. For instance, in my masters. I mean, right now, I try to keep on top of things. Mostly, I do like I take proper notes in class, more than necessary actually, just to pass the exam. But my goal is not just to pass the exam, because what we're learning in the lectures, some of it gives me new ideas to explore. Maybe some of it is even relevant for my internship project. So so when I stay awake all night, and when I skip hanging around the city in the weekends just to write notes and solve assignments and exercises, that's boring, that's mundane, I don't like that. That's hard work, that's not smart work. I'm putting in the hard work. And maybe when I'm writing a, let's say, a 60-page report, when I don't need to, this was not my internship will start from January, this was not required, still did it. I wrote actually two reports. One was just a review, and the other I tried little original stuff, new stuff, mostly about Monte Carlo simulations, using Monte Carlo simulations to study heterogeneous geometric rules to simulate out of equilibrium polymers and all. So all this was extra. I mean, I was just supposed to do a bibliographic study on just some available models, like what is already there in the literature. I did that, and I went the extra mile. That's hard work, that's not smart work. No. So if you are if you have the mindset of smart work, you will always think about how to evade, like how to like somehow do what I need to do in the least amount, but by putting in the least amount of effort. That can maybe help you stay afloat for a bit, but that cannot really push you to do the extra work, and like to do real shit, right? Then, apart from the project here, the internship project, I am doing like my own ideas. I work on the emotional modeling and all the stuff that takes effort. That's not just smart work. Making the slides, going to conferences, and night after night brainstorming, it gets frustrating at times. It's also not good for my, I mean, sometimes I don't get enough sleep, sometimes I, like, and anyway, so I don't want to go into all of that, but it's difficult. But at the same time, it gives me satisfaction because I am working hard and I'm proud of it. I mean, personally, I would be proud of being dumb, but yet work hard. It's not like blind hustle or that kind of thing, but working hard with purpose while being a little dumb is better than being so-called smart and all that kind of thing. For me, at least, there is no way around hard work. I firmly believe this. There is no way around hard work. Yeah, I mean, I think that's enough for this video. I mean, that's all I wanted to say. It's a bit incoherent, maybe, but okay. I mean, thank you.